what we are talking about is converting odd to part directly. That's very important starting point, which we saw yesterday. And in fact, the transformation happens in a very interesting way, you know. So the idea or sketch that has to be virtually modeled, then it has to be triangulated, and then it has to be given to a 3D printer and printed, you know. So the triangulation is a kind of a compromised model, and you are going to do a slicing of this virtual model, and we are going to put back these layers one upon another, just like what you see here, the sliced data getting accumulated, and this is going to give you the physical product, right? And in fact, the printer is the device that puts these layers back, and that's how you are going to get a physical object. So it is putting back simply those layers. And in fact, 3D printing, what we saw today just now, can be one of them, but there are generic many 3D printing technologies. Some classify as 20, some classify as 30. So when all these nomenclatures and classification went on, the ASME and the ISO guys, they wanted to bring in some kind of a standard, and they said, okay, nothing doing, let us have cluster these, technologies together, and we are going to have. So 3D printing is different to different people. For some people, 3D printing is the one which uses filament. For some other, they say it is actually uses liquid. And for some other, it is a technology which uses powder. In a way, they're all right, they're all correct. But these are the different manifestations of the same technology called 3D printing. Okay, so you have SLA, you have SLS, you have FDM, you have LOM, you have binder jetting, you have metal jetting, and you have direct energy deposition. Okay, so uh, let us see the definition of 3D printing then. So 3D printing refers to a set of technologies. So it is not just one, okay? And what exactly it does, it fabricates 3D object. Very important. It is a 3D entity which you can hold in hand. And from where it will do using a digital input data. So data has to be digital. And how it will build layer upon layer. So what is this digital data? Digital data can come from a computer model, or it could be from a scan data taken out of a point cloud data from a scanning, or it could be from medical image. Okay, all of them are the inputs which go in, and then it's all processed, sent to a machine or a robot which will simply print it, and you get a physical object. That is the definition of the technology. And what you can see here is the pioneers of this technology: Dr. Kodama, Chuck Hull, Paul Decoid, Stephen Scott Crumb, and in fact, it doesn't stop there. There are many more people, and many more. We are going to create new technologies also. You know, and it all started long time ago, 34, 36 years back now. As the time going on, changing. You have Charles Hull, who actually had this first mission made and first product developed, right? And so after this, there is no looking back. So this is the first technology called VAT photopolymerization. So when a monomer is exposed to a UV light, it takes the energy and begins the polymerization instantaneously. So it's a photoreaction, photochemical reaction that is occurring, which is used in this particular technology. And you can see in this animation how the laser is directed towards the vat, which is a tank, and with a galvano mirror, and you can see the built product goes down, and finally ejected up. And you can see here how the ejection happens. The perforations, what you see here is because it's not act like any piston, to minimize any kind of buoyancy or drag. They have perforated this platform. Very important. And next technology is powder bed fusion. In fact, this is the most uh, marvelous of all technologies, powder bed fusion, because it doesn't require any support. You can do something uh, which are impossible to make earlier. So that kind of products you can do, wherein product can be of any complexity, no matter what, you can do it here in this. Okay, and you can see the large system. Let us understand how it works. So it also works on a laser. Here it is CO2 laser, and the temperature much lower, and the energy also is less. And you can see here the powder is sintered instead of liquid. In SLA it was liquid. Here it is powder, and the powder. Let us zoom on to the powder, how exactly this happens. You can see here the powder particles get fused. They are not really fully melted, So many a times SLS remains a little bit porous as a technology, with powder, polymer powder, metal, by which we many times start taking care of secondary operations to fill these gaps, right? And you can see here how the bed is compacted by a roller which moves to and fro, and like a phantom CO2 laser draws the concentric circles, right? That's how it is. And after doing all this, we are going to get a cake. The cake is ejected out like this, and we extricate the products as though it is hidden inside, like archaeologists. We dig it out, remove the powder, extra powder. So wherever the laser has hit, it becomes solid. So by which you can make any products. So wherever layer upon layer, the powder gets sintered, that gets stuck, And in fact, the energy of laser is kind of a Gaussian distribution. Okay, it will penetrate into some depth. So the top layer and bottom layer gets stitched with each other, or glued with each other, or stuck with each other as they go down. That is very important. And here we have a small. This is Fabex is a powder-based drug production unit. You can see here how the powder is placed, so you can understand the SLS in a better way here. And you can see powder is leveled. There's a machine called Tech, and you can see the laser scanning something like round ones. They are sintered things. They are trying to actually print drugs. That means a pill, like a crossing, right? And after it's all done, they filter the powder to take out those particles. So it's very similar to your SLS, So you can see powder is being removed now, and these powder contain the pill which is already sintered. Okay, they are removing excess powder, they're sieving it, and you can see those small little things are the pills which are sintered. Some of them look like a donut, correct? Now, so you can see how this technology is really making deep inroads into various sectors like pharma, for example. Now, next important technology is material extrusion or fused deposition modeling. And here we use a uh, filament of polymer. It could be largely they are thermo plastics, and sometimes we use a monofilament, or sometimes we use bifilament. When I was in CPDM IIC way back in 2000, I was working on the project Prodigy. It's called Prodigy from Stratasys. It had two spools, one for build, one for the support. Okay, we'll come to that later. But basically, this is a filament which is extruded, and with a hot head, it comes out like a consistency of a paste, a very thick paste, and it gets deposited. And the print head moves, and as it moves, it covers the area of the one layer of the product, and that is repeated. There could be some communication disturbance now because the heavy rains outside. Okay. Moving forward, you can see here make a boat, which is very similar to FDM clone uh, uh, technology, building a part there, right? And then you have next technology is called sheet lamination or laminated object manufacturing. It is a wonderful technology, but technology could not be sustained because market somehow did not, buy this and support them. Okay, and it took another avatar using paper, and what you see here is orange one. It is actually made up of paper, and as the paper is cut and pasted one upon the layer upon layer, there is a printhead which also colors it. Somehow even this did not get any good traction because there is no industrial application of this. Largely it can be used for making some mock-up, and that's it. Okay, it cannot be used in industrial setting. So this technology was kind of rejected by market second time also. It has again come back with another avatar. So we need to really appreciate the original company called Halicis got shut down. They still own the patent, but unfortunately, it could not be sustained. And next, very important technology is called bind. And so they're able to do the same thing. So they have a each layer gets a coat of white and then color. So they are also able to make colorful products. But one difference is they are unbreakables. Okay, you can see here how the powder bed uh, is plotted, and it is powder is being removed, and you can see again and again this process. The first day, write the sections layer upon layer, and this is like just like a plan. It looks like. Then you just suck out all the powder, eject the table up, and you can get the product. That's how it works. It looks very magical, right? So it is very analogous to your SLS. Only that here adhesives are holding the powder together. There it was laser, right? Moving forward, we have yet another great technology, that is material jetting. So here instead of binder
Hello, sir.
jetting
I have
or glue
unmuted.
jetting, here material itself is put on the substratum. So how do they do that? They use a piezoelectric hammer by which a photosensitive paste-like material is deposited, by a large printhead, and because of which you can do things which are, you know,
Good afternoon.
pre-assembled, hard and soft, transparent to opaque. That kind of,
Yes, sir.
variety you can bring it within the same part. You can see a floating manifold, what you see here, as though it is a zero gravity. That actually shows a neoprene rubber-like
Hello, sir.
o-ring, which is very soft. The manifold, which is in light gray, is very strong like
Okay, sir.
ABS.
Okay, sir.
And the
Right, sir.
bottom actuator is also like
The same link
ABS,
I will send to
strong
students,
inside,
sir.
but to touch it is soft. That means it has got a
Okay,
cover
sir.
of
Thank you, sir.
soft material. All such things are
Yes, sir.
possible with
Through
the
that link only,
polyjet
I have opened this
or
class, sir.
multi-jet, material jetting
Yes, sir.
technology.
Yes, sir.
It's
Thank you, sir.
wonderful. In fact, we can make a lot of things
Yes, sir. Yes, sir. Thank you,
in
sir.
medical models and all that done very easily using this technology. You can see here how this technology, the material comes out like a paste, gets deposited, and you can see as it gets deposited, there is a green toward the rear. That is the UV light. You know, this is also photosensitive. Uh, you know, so let us see how it looks on a mission. See, this is how it looks on a mission. Okay, so the UV light is actually curing. So the traverse is so fast. And after this, you have direct energy deposition or electron beam melting. So people have been repairing castings and all by welding and all that. By heat, they're able to melt and pour and correct a depression or a kind of a pothole or a blowhole, whatever you call. Pothole is the roads, Indian roads. For casting, you have blowholes. That they were repaired by using a welding, by melting in situ kind of thing. So using the same technology, using various energy, it could be plasma, it could be laser, it could be, all this. Uh, People have been trying to build objects, you know, and that's how the direct energy deposition is uh, working. Will let us see more of it. I'm sure you will hear more about this technology in the other classes, and you can see here how exactly the powder gets molten, and there is a solidifying layers. There's a heat affected zone, uh, and the whole thing, the density of powder once it is molten is very heavy. The part will go down, it will sink. So 3D printed, though it uses powder like SLS, in metal printing we always have a support for two reasons: to anchor it to the substratum, otherwise the powder, the part will move, because it has got a different specific gravity, and it can move, because of the inertia also. As the table moves, this also moves. The powder density and the finished part density are different. So because of which it becomes like a two different body. So in order to anchor it, they'll have support, number one. Number two, they also have support to scavenge heat. Becomes very hot because if we don't remove heat, it becomes warpage will happen. So metal, though uses powder, invariably they have a lot of supports, which are undesirable, but it is a necessary evil without which we cannot. But there are some technologies coming without support also. For example, here it's a powder bed fusion. This is not direct energy deposition. It's very similar to SLS, and E-beam is also a similar one. We have lens and we have two photon, so many other technologies which are using plasma and all that, right? And here you can see how part is getting sintered. In fact, GE additive, the people who actually built these, they identified some two good technologies. They bought it over. One is the concept laser. I know what you see here is a concept laser, and the other one is the ORCAM. So these are very good for research. In fact, it's called research lab. And what you see on the left hand side is the research lab missions, and on the right hand side you have serial production capability. These are the missions which will actually go for making end user parts. Very important. In fact, in ORCAM, you have a lot of enablement for Industry 4.0 because they're able to embed a lot of sensors in the system, which will give you data, be it for the digital twin or for the condition monitoring or the in situ detection of defects, etc. It can, over IoT or IIoT, can transmit data that once you have data, you can actually control it. Correct? No? That is real-time data. So that's what these guys are doing. And in fact, they're incorporating this in a lot of GE's engines. And in fact, metal has a lot of other technologies also. Today, unlike in the earlier days, we have a lot of new technologies available at various price points, various capability. Each one they have their own special application. Here, not able to hear. Are you able to see the slide? Okay. It could be because of the rain outside. Shall I switch off my video? I have switched off my video so that maybe it will give us a better bandwidth. Okay. So what you see here again, a robotic arm depositing something, and the definition of layer upon layer is also a little bit, uh, questionable whether we should really incorporate in the definition or not. You can see here, this is like a print head, which will convert any kind of CNC into a metal 3D printing machine. Okay. What you see there, conical head receives metal powder on either side. Okay. And in the center, you have the laser coming. It could be a laser or a plasma or whatever. And as it comes down, the molten drop of metal is deposited on the substratum. Okay, that's what happens. Okay, and with this continuously pouring in sync, we are able to deposit and make objects. And here we have the same thing getting demonstrated using the same head. It is not exactly touching it, but not able to hear. Oh, I see.
Sir, no problem. No, no.
We can hear him, sir.
Okay, okay. I was worried. Well, so you can see how it is getting. So these are all the technologies which is changing. What I say is 3D printer in a box will go away. More and more 3D printers will be from this kind of concept where robots can be used not only for this, for many others. So there is no need to have a special 3D printer and all that. So that's the way things, technology may move. And you have this, a 3D doodler pen, which is available for less than 2,000, 3,000 rupees. And you can order online. And I want to ask a question. Can we call this as a 3D printer? My dear faculty and students who are there, can we call this as a 3D printer? This is analogous to your FDM. The filament goes on the top, it comes out, and there is a hot tip, and where it melts and it becomes uh, paste-like, and you can deposit. That's how it works. So can we call this as a 3D printer? I'll show how it works. Here you can see how it works. Okay, can we call this as a 3D printer? Hello? Can any of you can unmute yourself and tell me the answer?
Yes, it looks like a 3D printer, sir.
Looks like a 3D
Not
printer.
sure that exactly we can call it or not, but its features are quite similar.
Anybody else? Anybody have a difference of opinion?
Sir, I think it is not 3D printing.
Yes,
We are
you're
not
right.
giving any input drawing or CAD
Correct.
file.
Correct. Not just drawing, it is input CAD is not given. And so you cannot produce it consistently, same size, same thing again and again. It is actually taking data from your head and it is going to a hand and you're holding it in hand and doing. What happens if I give this to a robot, you know, then can we call that as a 3D printer?
Yes, sir. You can call it maybe.
No, you should not have any doubt. So if this is given to a robot and robot gets the data from the CAD, you know, and it is going to maintain the consistency, build after build, then even that can be called as 3D printer. Okay, just now we have seen the examples. Okay, very important, you know. And bioprinting is also there, bioplotting, bioprinting also. People have been trying to do a lot of things. We call these as trying out, you know, trying to make it, fake it before you make it, they say. These are not real. They're trying to build things. Probably one day will be uh, able to do some tissues, organs which will function. But at a basic level, what they've done is some cells which are mimicking some function, like the organoids, what you see in the bottom, you know, right hand bottom. No, these are twitching cells, you know, and is actually built on a cell culture which is 3D printed. Correct, no? And so this, for example, this is additively made but not 3D printed. Okay, and so एक एक बूंदी को बाइंड करके you know sugar syrup से you are made into a spear. Okay, this is laddu, and laddu is additively made but it is not 3D printed. So there are a lot of things additively made. Can you name something more than this? What are all additively made but not 3D printed? Again, a question to all of you. Well, there are many, you know,
So there is
buildings are
it actually.
buildings. Our buildings are all built of bricks, right? The bricks, they are all additively. Building is built additively, but it is not 3D printed. It can be 3D printed also, but it is not 3D printed. So the whole thing, you know, whole world, you have, of course, when you go into mm, uh, quantum theory, it becomes energy, but if we don't touch upon that, we still call atoms, molecules, or building blocks, right? They're all additively put together to build this world, what we can see and touch and feel, right? So additively made many things are there, including plating, cladding, painting. They're all additive only. Casting is additive, and you know all of them are additive. No? Many of us think it is not additive. So even plywood, for example, is additive. We made thing. Well, moving forward, Dr. Adrian Boer and his team, they started mooting a idea of 3D printer printing itself, establishing a connection. A parent builds the child's parts and you assemble and you get, you know. This actually opened up a open source revolution, and soon a lot of them, the magazines carried this cartoon 3D printer printing itself, making a small, giving rise to its offspring, you know, kind of. But today, this has led to a new range of technologies being done all over the world. Correct? No, many, even in India, At Hyderabad also, a lot of people are doing, for example. At your own institutes, people are doing. Because this technology, the patent was expired by 2009, and people started accessing how to build it, the know-how, and it has become a open source now. So open source actually helps actually to bring a lot of new technologies. Like what? Like right now, Status is discovered or patented a Cartesian type 3D printer where the table moves XYZ. But you have Delta, you have Polar, and you have Scara. These are different types of technologies which are fundamentally based on the FDM principle only. But the way they deposit the build is different. And while open source brought a lot of accessibility to people, the reliability is a big issue. And this is what is now being addressed. Today, we have a lot of desktop missions coming, okay, in every possible technology because slowly and steadily the patents are getting expired, you know. And so you have even the SLS, SLA, FDM, they're all coming as open source things, and people are building. And a few makers of these open source uh, further developed, and they made a very sound technologies which are dependable, reliable, okay, like these ones, okay. And in fact, you can think of on one side you have a low cost mission, on the other hand you have a production mission which is highly reliable. So for adoption, we require something which is in between. And that's where I think the Form Labs have brought in a lot of new things which are really good. You know, what started with Form 1, Form 2, today Form 3, Form 3L, and the Form 3B are all making great products, and they're highly reliable, and they give you production output just like a big system without any much investment. So that's what is going to actually help adoption, you know. And so you can see additive manufacturing is now getting consolidated as a sound mature technology. It is making deep inroads into various sectors of industry, be it jewelry, medical, FMCG packaging, lifestyle, architecture, automotive, aerospace, white goods, electronics, electricals, plastics, and whatnot. And in fact, people are trying to print big things to prove a concept. And so much so in Chennai, they have built those houses you have seen. Okay, a big news, and people are also trying to print very small. This is in IIT Kharagpur. You have a nanoscribe, which is building. This building, what you see here, is the IIT Kharagpur's main building, administrative building, which has been built. You can see in the bottom the green scale, which is 20 micrometer. So with that scale, we can as well understand that these vertical lines, thin lines, are sub-micron size. In fact, whether it is small or big, you know, a 3D printer is having a potential to build a lot of big things also. So like a Lego, you can cut the part digitally and make it on a humble printer like what you see in the foreground to build a mammoth, you know, which is in the background by actually gluing together the many pieces. Today, glues, there are very good glues available, and you can always depend on them. They won't fail at all. And industrial scale 3D printing is a big game changer. It is going to be um, uh, uh, looking like this, what you see here, you know, a form of different systems. They build 24 hours, 365 days. They can be remotely controlled even during a pandemic like this because they can have a so-called Industry 4.0 kind of connections. Well, in fact, the 3D printed object, when it is built vertically, doesn't have any problem. But once it takes a organic form or a slant, the layer thickness is going to really contribute to define the resolution. And just like how you have a concept of a 2D pixel, 3D pixel also very important. And 3D pixel, how big it is, determines the accuracy with which or the resolution of the part what you build. So as we are talking, you can see what is happening. The staircase effect, how it is building up, and you can see the thickness, how it matters, you know. And this is the 2D pixel, and then you can see the 3D pixel. This is 3D pixel, what you see here, okay. And you can see 3D pixels also, how resolution can actually contribute to the. And now let us classify. We have touched upon all types of different technologies now, which are basically a photopolymerization, which uses some kind of liquid, and then you have direct material melting, FDM, or freeform fabrication. LOM uses sheets or laminates. Directed energy deposition, you have the lens and EBM. Binder jetting uses binder. Metal jetting uses different types of paste-like material. So you have different types there: MJM, polyjet, direct object, DOD. Then uh, we have NPJ, and we have powder bed fusion. You have SLS, DMLS, multi-jet fusion, E-beam. They all come under. But in all this, we also need to add bioprinting, which is yet another kind, which cannot come under these, but there it is also there, and that is also 3D printing. And okay, I think this slide should have gone earlier. Well, we will now look at support, which is very important. Support is inevitable. Many times the cantilever cannot be sustained. So you need to have scaffold, which will help build things which are at a inclined fashion. And these are all some of the tools required to remove the supports. The main function of support are one for thermal dissipation, printability, and for the part balance. If a part is very heavy also, I cannot build it on one scaffold. It will start, having, its own bending moments. So we need to support it, simply support it on either side. And you can see here, with a dual head, sometimes we achieve supports. You have two different heads. One is a build material, the other one could be a support material, vice versa. Or it could be both build materials where you want a two color, product which doesn't require any support. Could be, and in fact, these are all breakaway supports, what we call. I think there are some slides which have gone back and forth. I'm sorry about it. These are the two types of linear supports. We have one which goes like a scaffold directly. The other one is like a tree-like support. And the beauty of tree-like is it is very minimal. Linear support, you can see it wastes a lot of material, and also it takes more build time. A tree-like support, just enough, sufficient support it will take, and to clean it is a lot easier if it is tree-like. And you can see here, it is also productivity-wise also, a better support is a good solution, because the cycle time also gets reduced if you have a better support like a tree-like support, which is exemplified by this slide. You can also have a dissolvable support. Dissolvable support we use in jewelry and all, where wax-like thing, one which melts at a very high temperature, one which melts at a very low temperature, like a paraffin wax, are used. The same thing is used in the material jetting also, object or conics missions. We use a water-based, PVA which is melting, as soon as you put it in the water. Let us see. See, this part is actually a very complex part, which is put in the water, and you can see it is all getting disintegrated. As you remove it, you know, you're able to use it with all its complexity. Okay. And in fact, we also have technologies which give supportless build technologies. What are they? So they are very much like your 3D printing doodler. Okay. So here we see this is a very funny thing. No, this is like a doodler, but only thing is it is driven by the 3D print head, not by hand. You can see here it is going up in the air and building all this. And this is a polymer. Okay, probably it is building a scaffold like thing, but it is a product itself. It is like a scaffold. You know, it is making a bridge. So it's taking the other side. One side is done, the other side it is building now. So you can see there is no support here. Okay, this is something which is really good, and so all of you can also research on this. Looks so easy, isn't it? And you can have a lot of such things. Uh, of course, it has to be strong, uh, not only look nice, but also strong enough with time. So it is bridging the two now, almost done now, right? So it's formed a kind of a bridge. That is the end product. You see, that is the beauty of supportless. In fact, there is one more technology where in the University of Southern California and Swiss Federal Institute of Technology, people have come out with some kind of a reusable metallic support. You may wonder how. So let us see an example on this movie, what we have. Are you able to hear the sound? Can you hear the sound now?
Efficiency for nozzle-based material extrusion processes. Inspired by pin art and Lego
You
blocks,
can hear the sound?
Professor Yang Chen's group at the University of Southern
Okay.
California figured out a novel support strategy and designed a programmable and reusable pin support. The work is published in the journal Additive Manufacturing. The main idea is to use a single motor to drive a large number of pins serving as a movable printing platform to different seat heights. The pins will be lifted if prefabricated hollow tubes of standard lengths with magnets are inserted from the base into the pin rods. For an arbitrary CAD model, the researchers developed support generation software that optimizes the part layout on the platform to save material and printing time as much as possible before generating a toolpath. The software will also tell the user which tube or combined tubes to select from the set and be inserted onto which metal pin. When a printing job starts, the pins with inserted tubes will move up by one layer thickness after printing a layer. For a metal pin at a certain height, 3D printed material can be deposited on its top surface. The experimental results of several test cases show an average of nearly 40% saving on the printing time and material with increased reliability and robustness. When the printing job is done, the pin support can be easily removed from the built parts without damaging fragile features since each pin top is a washer connected by a magnetic ring. After peeling off the attached washers, the created object is separated from the reusable support. The pins can be reset to their initial positions automatically. Finally, the pin top washers detached from the 3D printed object are inserted back to the pin tips. Now, the reusable support is ready for another printing job. The researchers would like to investigate the reusable support for the big area additive manufacturing, which may provide a feasible solution to significantly reduce printing time and may be applied to construction and furniture 3D printing. For 3D bioprinting, the researchers envision a further increased saving on expensive bio-related materials with a reduced pin size. The researchers will also extend the reusable support to other AM processes such as projection-based stereolithography and powder-based selective laser melting. The reusable support could provide a new direction to address support-related issues in the future.
Well, so there was a,
Additive manufacturing.
I think we'll now focus on a little bit of materials. I'll not go deep into it since it's already covered. And you can see still metal is very small percentage, but it's going to increase. And the technology is steadily becoming faster, as you can see. With SLA, Apple to Apple comparison, 11.5 hours, SLS 3.5 hours, PolyJet 3 hours, to clip, which is 6.5 minutes. So what is the comparison? So it is only expected to increase in speed as we go by with the technology. And let us now jump into some of the case studies quickly. I'll not explain too much in detail because they're all part of clients, but they've permitted us to use these. You can see some of these unpainted and painted, how they look. A core model. This is like a burnout model for a casting lost wax process kind of thing. Here it is made up of nylon and it can be burnt out at a particular parameter. And these are also similar things. This is all glass-filled nylon material, very strong and they have a high dielectric strength. So it's a footwear liner. And how we are converting metal to polymer, nylon. Now you can see the way it is transforming. And in fact, these are all end user parts. Very accurate. They're end user parts. They can actually survive the life cycle of the context of use. Very important. Again, here, this is a glass filled nylon. Number of parts. You can see it's a particular type of bevel gear that is all printed. And this is all going for end user application. This we have seen yesterday. So some of these, actually the part is cut, and it is glued together and then it is painted. You can see there is a pencil here to show the size. So including the dashboard and all we can do. This is a car side door interior. This is a kind of a dashboard and there's an electrical product. This is a large part for a kind of a reactor. And these are all mirror optics for automotive lamps and those accessories. And these are some of the finished products. They look like they're a final product, but they're all 3D printed. You can see some of these mirror optics. This is an IoT device. So as built on the left hand side, you can see how it looks. On finished, you have these. And this is an IoT device which is made in hundreds, and they don't have a tool at all for this. So because after they use 100, they will change the design. So that's how it is. So they don't want to have a tool for this. And side is a health band. So this startup, they approached us to make these for Kickstarter, pitch. So they need to have these functional products presented live. That's where we help them to make these. And this again, a IoT device, sense, think, and fix. This was developed at Imaginarium. And you can see some of these. This is a new avatar of the same product. This is Blue Star's IoT device, which in fact got an award. And this is all made at Imaginarium. And this is Bempo's hyperthermia monitoring device. This is also made at Imaginarium, where we have to develop a new material which is infant screen friendly. Very important. This is a portable breast scanner, and of course we did the exterior, not the interior technologies. And under jewelry, we have done a lot of work, and this is the process flow sketch and convert to CAD and, as resin print after if, polishing and studying it with diamond work looks. Some of these are visualization actually. Many times today, companies only keep these virtual models, and whenever they get an order, they will transfer it to us. So we are the manufacturing partners for a lot of such outlets throughout the world. We have the best competency there. So you can see the new aesthetics, how it is changing. Lightweighting, for example, can be done in jewelry also. And you can see the complexity of this. So this is a design entry which was sponsored by us. And you can see these are some of the designer accessories made for a particular designer, right? So here is yet another connection for yet another design group. So these are matching the chudis of the traditional bangle worn during the marriage, particularly in North India, UP, Punjab and all. So matching that, these are the finger rings which are made with the matching enamel, very important. So it's an experiment done by Pallavi Verma, one of the designers from NID. She has played with polymer and metal, nylon and gold, something like that. You can see the same thing, different versions. Fundry is another startup. They wanted some jewelry using primitives, like a wire frame. You can see some of these directly can be taken and made into a jewelry. So people, and these are not very heavy. They're made up of nylon, so they are very light in weight and but strong. They can be finished. They can be plated. So the complexity with which we can handle it is not only just 3D printing, but also the skillfully finishing them is very important in this. Because you can just think there will be a lot of support for this building. Otherwise, we cannot build them. So it has been managed very well. And this is a custom jewelry where the boy and the girl, they spelled out their names that has been transferred into a waveform that has been placed on either side. Boys one side and girls the other side with a, this is platinum and diamond and gold rims you can see, very expensive engagement ring. And likewise we make a lot of such custom products. So this is also very complex, you see. It is like a cage like thing. So this has been made possible by investment casting. You can see this again, complex, quite complex pieces. Again, can be 3D printed. This we have seen yesterday. You can see how complex this kadai is. Okay. Again, it is wax printed and then cast in metal. So these are some of the titanium based pendants, which will go with a black choker like that. You can see the titanium metal, which is quite exotic, and people are quite fond of it in Europe. And some of these lifestyle products are also um, being developed. They have a lot of dramatic way because they move. They give as though they're getting, they're growing. in size. Here also, it looks, because it is moving on a turntable, it looks very different. Collapsible chairs and all, these are some of the things which are very good for the um, lifestyle products. This is again a kind of a sofa or a chair, easy chair, all rolled into one. It's very soft. When people sit, it will little bit yield and accommodate their body form. You can see here how this guy is relaxing. Again here, it is soft on the top, but inside it will be hard to sustain the whole thing. These are some of the ways people are trying to build textiles. Yesterday there was a question on this. So people are trying to build. So if it is a hard part, how can we make it flow like a textile? This is how it is. It is made up of small units which are all assembled. While we don't assemble anything, it's all printed as one. And you can see here, again, depending on the size, one can have something like this or something like this. This is SLS built. So these units are all connected to each other. They have some kind of a fluxing that is possible. See here again, it's 3D printed. Each unit is 3D printed and assembled. You can see here again, it's like a rubber-like material. This can be printed. When you go very close, you'll see the reticulation. They will have hinges, which are all very functional. Here also, this cloth is again made up of nylon, and if you go closely, there is a small triangle-like thing. They have fluxing joints, and that's where you get a perception of flow of cloth. And in fact, in jewelry, lifestyle, and fashion, a lot of things we have been doing for a long time. This is my own design, peacock headgear. We went to Asia's first 3D print fashion show, and we have later on opened up a kind of custom trophy. We have been doing a lot of, trophies like this one. Okay, these are all made of. Again, here this is made for CII. This is a black lady. The 59th Filmfare trophy was all done by 3D printing enablement, and we made 42 pieces. There's one limit sample available in Imaginarium now. So we can see how the bird has transformed into a blooming lotus, and that's the new design, which was then converted into a artifact. We do a lot of collectibles like this, trophies. Coin medallions, then it's a wobble head, and in healthcare, interestingly, we do a lot of work. So the starting point in medical is an image data, okay? And image data is typically a slice data. So slice data, if you put back, you can actually arrive at the volume of that section. And using some softwares like Mimics and all, Osirix, we can isolate these. It's called segmentation. So you can see here, medical CAD CAM, you have two outputs. One is a digital model where you can explore on screen. The other one is a 3D printed model which can be held in hand, and both are being used in the industry. DICOM is a image standard. It's a protocol, and will not go deep into this. You can see the segmentation workflow. So this shows medical opportunity what you have. In fact, this is changing every day because I've introduced many new things here. At level 1, you have devices. Level 2, you have anatomical models. Level 3, you have guides and fixtures. Level 4, you have implants, and then you have drugs in between, and then you have tissue. So tissue is something people are actually toying with it. Still, they are not able to fully provide us any living tissue from this route. They have been doing in vitro studies right now. So it goes. I don't know when this will be ready. People are trying it out. It's very important. So this is what we talked about in the beginning of this talk. The organoids are tiny self-organized three-dimensional tissue culture that are derived from stem cells. Okay. And they can be groomed into a particular function, in which case this is like a heart. You can see the twitching action. We also done a lot of interventions in dental. So this is a set over correction, cranial implant. We have done as many as 9 projects, and you can see the amount of restoration that has been made just because we could 3D print. Then you have a lot of implants for mandible. We have done. This is for fibular reconstruction. We have done. We have done anatomical models. Here on the top right hand side, you find a white portion. That is actually the tumor. You know. So doctors, clinicians could actually isolate this and operate, save a lot of kidney, natural kidney. That is very important. And we have hand cast, a lot of these surgical guides. This is the heart sections. And during COVID time also, we have done a lot of work, such as what? Such as full phase protection ke liye, which we did. We also did splitters for ventilator. You can see how they are applied. These are venturi valves. So this is a fabrication. There is no 3D printing here, but agility you should have to serve. No, an end user doesn't really wait. He doesn't expect something to be 3D printed only. Whatever is good for the purpose, we should be doing. So some of these are all 3D printed. And we have also been doing a lot of things for birds and animals, pets. So here you can see how a beak, broken beak has been fixed. This is an artificial beak. What do you have? So the future 3D printing scope would be the hardware, as we discussed yesterday, will be saturated. Material and software becomes a big opportunity. You can see the same thing has been done. These materials and software are the big areas now to focus on. And additive manufacturing itself is a important actor in Industry 4.0, as you can see. It brings the physicality of the cyber physical system, very important. With that, I think we come to the end of today's presentation. We have been enabling industry, creating value, using all our technologies. We have people, skill in order to cater to the needs of the industry. At this point, I would like to stop and take your questions. Over to you now. Hello? Yeah, we have come to the end of the presentation. Yeah, I'll be happy to. Right. Yes. Yes. Thank you, Chatterjee.
Hello, sir. Good afternoon, sir.
Please, please.
Sir, all the additive parts are need not to be 3D printed, right? 3D printed. And what are the criteria?
Additive, see, additive means all additive. See, additive is a larger umbrella, you know. So in the manufacturing, if you see, no, there are plus processes, additive processes, minus processes. You have all the conventional, then zero processes also. What are zero processes? Like you have coining, rolling, wire drawing, and hobbing, forging, and all these are kind of a forming processes. They don't have material. Material is not removed or added. You know, in coining, for example, material is not um, removed. So it flows plastically, into the cavity. That is the whole beauty of it. And so they are called zero processes. So in additive, we have so many things. Adhesive, you have like a brick and mortar, you have all this of additive only. Plating, you have casting, you have even powder metallurgy is a additive process because you're adding and compacting. And so they're all additive only. All types of casting, injection molding, die casting, pressure die casting also is additive only. So 3D printing is a special kind of additive. Okay. But today, synonymously, they're telling everything is additive. But as a practitioner of this technology, I would like to differ from that, define it as a digital fabrication. Okay. 3D printing word, additive manufacturing word, is a loaded term. Additive manufacturing means what? Making millions, right? So this technology even today is not capable of doing that. Not viable. Why would you want to do it? Want to make millions when people don't want it. So I don't think in future the customer will want million things because they want to enjoy their own different things, right? So uh, I think AM or 3D printing should be replaced by digital fabrication. Most appropriately. Word. Hope I've answered your question.
Sir, what are the criteria that we need that are required to say additive parts to be 3D printed parts?
Additive parts to be 3D printed. You mean whatever way it is produced, you want to 3D print it now?
No, sir. What are the
So
criteria that are required to say that 3D printed parts as a additive parts as a 3D printed parts, 3D printing?
well, you additive or any other way, if you want to replace that with 3D printing, you do it only when there is a need for you have a better value creation. If you don't have a better value creation, I think it is better to continue with the way you are doing it earlier. Okay, we can do it only when, suppose you want to have a tool in which I have a core. A core cannot be cooled easily, So in the olden days, the core was never cooled, It's very slender or whatever, no. They were only cooling the cavity. Okay. Now you want to have a conformal cooling channel. There is no way you can build such things, because your drill cannot go in a curved line. Drilling is always straight. So that makes it necessary to adopt this technology because you want to have a curved cooling channel. Then you may require. And again, you want to do a organic form. It cannot be CNC milled or it cannot be injection molded. It cannot be metal injection molded also. You finally resort to 3D printing. So I think these are the two areas where you plan to go for 3D printing. But before any time you apply 3D printing, you should have a big question. Why I want to go for 3D printing? Very important. You can ask a number of times why. Japanese said 5 times you have to ask why. You know, but unless you get a good value, you should not go for 3D printing. So 3D printing is a technology you only go for when it is required. It delivers value, and that is very important. Yes, anybody else have any queries?
Sir, hello. Are you getting
Somebody
my
is
voice,
asking
sir?
of presentations. Okay, presentation will be given. How the design mindset should change when one moves from conventional to digital manufacturing? Very, very important question. Huh? It is by Hiralal Singh. Okay, Dr. Harlal Singh. Okay. Well, I think uh, you must be from MNIT, Jaipur. Harlal sounds very familiar name. Well, correct, correct. So basically, we need to understand if the product is very complex, you go for 3D printing because there is no other way of making it. Number one. Number two, you want to have a conformal channel, pulling channels. Again, a task which cannot be done by any other process. You should go for 3D printing. Or you want to have a kind of a scaffold, a very organic form, which cannot be milled and it has got a lot of undercuts. Then also you may go for 3D printing. So these are the areas where you can context of use where you should go for 3D printing. A conventional nut and bolt washer or anything should not be taken and converted into a 3D printed object. No. So in fact, we should forget all this, unlearn all this old way of making. 3D printing means a new design thinking has to go into it in order to derive the best use of the technology. What exactly technology offers you? The consolidation of parts is a capability. You have to look for that. Is there a advantage consolidating? When you consolidate, many times, no, people say, what happens if I have a top portion fails, bottom portion is, intact. Now it's broken, but you have printed together. Now it's a fused part. I cannot have now replacement. Yes, such things also happen. So you need to be very careful. Suppose you are going to have a repeated failure, such parts you need to separate them, divide and rule them. If you fuse them together and because of practice you keep on getting defects and one side part is getting always defective or fails, it is better to keep that as a separate spare so that you don't have to again make whole thing, you know. So part consolidation, while it is a advantage, sometimes it can be a disadvantage also. So businesses, you know, the way businesses look at it is it really creating value? Okay. Now, lightweighting is another virtue. Payload can come down, but is it required or not is also important. Am I spending a lot of money because it is 3D printed? So I'll give an example. Yesterday I was taking this example. Distillery bottle hai. Distillery bottle cover, the cap could be mass manufactured, you know, by injection molding, and the cost is very low, right? Suppose you 3D print it, it will cost you one cover will be around 300 rupees, 400, depend on the technology what you have, the investment you have made, you know, in order to get this out. So that will be very expensive, and so it's not viable. So converting that is of no use actually. Just to prove some point you can do, but I don't think, you know, unless it matches the uh, conditions of use. Okay, wherever it is put, it has to function normally like any other material or the existing one. Number one. Number two, if it can be of a lower price than what is currently being used, then also you can go for 3D printing. You know, so 3D printing means because you have a technology, you should not keep on converting everything into 3D printing unless it creates value. And we see many times people ask, can I 3D print the lamp post? You know, lamp post जो रास्ते में रहते हैं. Why you want to 3D print it? No, if it is about 20 feet high, you know, so many layers will come. At 100 micron, so many layers will come. How long it will print? It will print for 6 months for a one post. So, I mean, what is the material? Material is all very costly material, because metal, when you print, uh, every gram what you print is much costlier compared to what you can melt and pour, because you have to atomize the powder. That is, powder is taken to a melting point and liquid. It is then poured, in vacuum, and they all get kind of they're going to become a cloud. It's cooled by a water jet from coming from below. In mid-air, they take a spherical form of 40 micron. They sieve it. Jada hai to wapas, they go into the recycle. If it is appropriate size is taken, saved, and then they store it. So yield is very low. The whole thing, the energy input and all, makes the material very, very expensive. So sometimes, no, we should think, we cannot have a lamppost made of 3D printing, because it is not worth it. Because conventional way, what we have is much better, like a drawing or rolling or your rotary casting or whatever. They are all much better and cheaper options. So that's very important. That's why I made a point yesterday. The manufacturing will take a backseat, because it's all driven by what the customer wants. The supply chain becomes a demand chain. Okay, there is no supply chain. There's a demand chain. Somebody in sitting outside in the globe, some corner, nook and corner, will order for it, and you manufacture on demand. When you manufacture on demand, it could go into CNC, it can go into 3D printing. As I said, these are all holy trinity: CNC, robotics, and the 3D printer. They come together. They contribute to all the manufacturing of future. Correct, no? Um, it's all hybrid. So where you take 3D systems, figure eight, or additive industries system, they're all a kind of a compound systems. They come with a robot, a set of robots. They come with a set of 3D printers. They come with a machining center all together. So the raw material bay, takes the raw material, and it at the delivery bay it is going to give you. So non-contact technology. See, in the COVID times, people use a lot of non-contact technologies. So in medical also, people use non-contact technology, because they want to preserve the sterilized atmosphere inside when it is being made. After the part is made, it is also sealed inside. When it comes, you are touching the part, but not exactly. You're touching the sealed cover, right? Sterilized thing. It can have a single or double layer sterilization, wherein there are two jackets which will protect it. So one for casual handling, the other one before going to OT, somebody is going to sterilize it, and they uh, provide it. So all such circumstances, you require, a closed system, wherein non-contact technologies like IoT and these digital technologies, uh, then traceability is done by blockchain, and people monitor in situ quality by again IoT and other sensors. So the whole thing, it makes it appropriate only if it creates value. Somebody should be willing to pay for it. You know, if they're not, then it's better way is use the conventional thing. You know, if potter can do a better job of making pots on a potter's wheel, so be it. Why he should 3D print? Because 3D printer has come. We have made a clay printer. I could have shown you that the clay printer was made at Imagine. But so there are so many things we can keep on adding. Maybe next presentation I'll add. We made a clay printer about 3-4 years back. Chocolate printers we made, but it's all for fun. Not for selling, but it gives you a capability, of mechatronics and all, how to control. Yes. Any other questions? Yeah. Can you comment on current scenario on the application of 3D printed components as medical implants? Well, there are many. Today also I showed you some. I went very fast. So cranial implant, mandible implant, so bone replacement in some areas we can do. Okay. In medical, there are different ways we use it. One as a bone if you want to grow inside the implant, we have a different structure for that. So we make it porous so that the bone can actually uh, go into it. There are materials which are called as bioabsorbables. So they are scaffolds which are strong in the beginning, but as they spend time in the body, they slowly gets absorbed. You know, by thereby leaving the natural growth of muscles or tendons or your bones to grow. What we call as osteo osteosis, osteoinduction, um, um, uh, all that, different processes are there which are going to be helpful in regenerative medicine, they call it. You know, people have been using in dentistry. People are using, and there is also another application of 3D printing, exoskeleton, that is prostheses and all, prosthetic devices which are put outside the body, not inside the body. And so people are doing, they are doing bionic hand and all that. So in ISC also people have developed, patented it. You know, some of them. So that is going on. Jaipur food is also being improved upon by people. So that's another very good uh, opportunity we have. And I think with that, if you have any more questions, I can take.
Sir, sir, actually, this is Dr. Suranjana. Sir,
Yes.
my question was like many people, particularly from the polymer domain, they are working on developing some biocompatible polymers with less toxicity. So, are there 3D printers, sir, which can use these as 3D printing ink for developing certain designs?
Yeah, absolutely. So 3D printing materials, a lot of work has been being done. Biopolymers, bioglass, and bioplastics are all being tried out. And they have, either they will stay as a inert material inside the body, or they get absorbed in the body. You know,
Yes,
such
sir.
things are being tested on in vitro. Still, in some cases, they are very happy, especially in the implants and all. People are happy. So we have made about 9 implants now, cranial implants. They're all inside the body. They are doing well, so no problem. You saw some case studies where a madam had lost her cranial plate and it was replaced, and
Yes.
she is fine. And she could actually come to Imaginarium and give a testimony, how she is feeling, how she is thankful to us. That happens very
Okay.
rarely. The patients don't come and give you testimony that they are now wearing the implant which is inside their body.
Yes,
So
yes,
that
yes.
is very good. So we have, likewise we have been doing on animals also. Many times pets and all, they come with a broken limb and all. We also try to see what can be done, with that. What best we can do. See, technology is there to help us, help to, help not only humans but also every living organism, be it a plant or a living cell or an animal or anything for that matter. So that way, 3D printing has been doing a lot of enablement, and in healthcare today it has become very, very important. Even the robotic surgery, robotic manipulators are being customized, on demand, and given to these robotic systems to handle. You know, so the patient's disease condition is first prototyped, the whole tool path like thing. No? Because you cannot try out on a live, patient. So many times they do a dummy and test out, and they practice, they rehearse, and that way they ensure it's right first time. There's no mistakes done. So for that also people are using a lot of 3D printing this thing. And drug efficacy is also going to get tested on artificial, human body parts, for example. So many people think that it is all ready, and no, nothing is ready so far. Okay, the vascularization of the tissue has been a big problem because uh, I cannot print. I cannot take a seed and powder it and make it into a bio ink and print a seed and expect that seed to grow again, germinate. We don't know. The God is playing hide and seek there. One day it may happen. We don't know. Right.
Yes, thank you. Thank you so much.
Welcome. My pleasure. Yeah, yeah. I think IIT Hyderabad is taking a lead in that. Yes. Right. Thank you.
Yeah, hello. Good evening, Dr. Ungar. Yeah. So shall we start or we need to wait? Okay. Okay. Yeah. Yeah, thank you very much, Dr. Onkar. Yes, like you rightly said, definitely we can they can extend the analogy and we can further discuss based on what is discussed on the toolpath as well. So I usually like this topic a lot, toolpath planning, but although that was not the scope, but however, please feel free if you have any questions related to slicing and area filling. So I'll be very happy to answer those also, along with the omnidirectionality. Yeah. So I think my slides are visible, Dr. Onkar. Can you please confirm one? Okay, thank you. So, okay, so well, good evening to all of you. Today we shall discuss about the omnidirectionality in additive manufacturing systems. So basically, I'll just show you one video before starting. This is how the conventional nowadays latest one, the DED system looks like. You can see that the center is a laser is coming in the center, and from the conical nozzle, the powder is coming, right? And then you keep on depositing the material and build the entire part. Is the whole part is built like this. Now there is a question: was it the same way when it was invented? It is not. When it was invented, it looks like this. I have already mentioned in the last lecture, Professor William Steen, when he invented the laser cladding process based on powder, the process looks like this. It used to have laser at the center, which is a CO2 laser, not visible to us because it's in the different wavelength. And this is the clad path, and you are just they're feeding the powder from side. Now, such a simple system has really converted to such a sophisticated system. Why? So that you will be able to have an answer. So, and this is about only DED. I am going to discuss for all additive manufacturing processes, and you will be having answers to many. Like for example, why do we use F theta lens in the SLA process, in the powder bed fusion process? Why the size of the machine of powder bed fusion is limited to 250 by 250? Why it is not really 2 meter by 2 meter? What issues comes? Why in the case of concrete printing, you need to rotate your head appropriately? So today you are going to have answers for all these questions, and you will find that there could be a common name given to this phenomena due to which these auxiliary arrangements are required. To know more about it, you can read my publication recently in ASME that discuss more about the the auxiliary arrangements for omnidirectionality in additive manufacturing systems. So basically, this today's presentation will focus on the introduction, not really in detail. Today, I'll just quickly finish it. Then, what is omnidirectional? What and how does the omnidirectional additive manufacturing should be? A proper definition. Then I shall also discuss about the inherently omnidirectional AM systems. Then omnidirectional direct energy deposition, omnidirectional material extrusion, wet photopolymerization, sheet lamination, powder bed fusion, material jetting, binder jetting, and all. And finally, uncalculated presentation. So basically, additive manufacturing, you all know that, but just let me just read this. It's a process referred to fabricating the object in a layer by layer manner directly from a CAD model. It is an automatic process of manufacturing objects, part, prototypes, tool, assembly directly from the CAD model without any cutter, tool, or fixture specific to the geometry of the object. I am sure you are aware already because the second day of workshop, but still, why we say that without any cutter and tools. So let me just take an example. I usually take an example here. Like for example, you want to make a cylindrical object which is having a hole. It is a cylindrical object of metal, and this hole is 6 mm diameter, and it is a cylindrical object. Now, to make this part, you will preferably go to lathe operation, and you need a 3-jaw chuck, right? And a 3-jaw chuck is sufficiently good enough to hold this particular object, and a 6 mm diameter drill bit tool. Now, if I change the geometry, and the geometry is no longer a cube, it is a cuboid, and also the diameter has changed. Assume that this diameter is now 8 mm. In that case, as it's a cuboid, more appropriate fixture to hold it could be a 4-jaw chuck. 3-jaw may not be sufficient, may not be good, very optimal. And also you need a different tool. So you saw that I slightly changed the geometry. I required different tools in the conventional process. But in the case of additive manufacturing, what we do, we just create the slicing of the object irrespective of whatever the shape it is having. The hole will be either larger or smaller, although you will keep on depositing it with the help of the same nozzle. This is the basic of 3D printing, and it follows in a different ways. How you are adding the material depends on the process. So basically additive manufacturing covers into 3 parts: pre-processing, build processing, and post-processing. Of course, there are 7 ways of building the part, and that is what is classified by ASTM. While in the pre-processing, we take a CAD model. If the CAM package you have is not capable, you have to convert it to STL file, and STL file is nothing but representation of the surface in the triangles, and then take a slice or intersection between the slicing plane and the triangles. As a result, you will get some contours. Now, whatever shape of this internal hole is, that doesn't matter. As a result, when you are building it, you will just leave either more material or even less material. If it is 6 mm diameter, less material will be left. The cavity size on each slice, if it is 8 mm, the cavity size will be larger. Yes, of course, in many additive manufacturing process, you need a support mechanism. Like if you are adding material at the center of the part, no issues. And if you are adding the material on the edge of the part, due to surface tension, it may sustain, but not really up to a very large extent. If it is larger than the required, the droplet will fall down like this. Hence, you require a support mechanism over here. Later on, it has to be removed. So the post-processing usually required in removing these support mechanisms only, most of the time. Also, sometimes we do, as we create that part by additive manufacturing process, we get a staircase effect, meaning to say we create an object like this with some staircase. Hence, you need to sometimes remove these staircases and create a smooth geometry, right? So this is additive manufacturing. ASTM has classified this process into 7 categories, which we have already discussed yesterday, and we have also seen they have classified them based on the energy consumption. The first is wet photopolymerization, least energy required, and the last one is directed energy deposition, highest energy required. Now, let me rearrange today. Instead of having wet photopolymerization on the left side, which is the least energy required, and directed energy deposition on the right side, which shows the highest energy required, what I'm going to do, I'm going to reshuffle them in such a way that I will say this left one is really a non-omnidirectional process and required some additional arrangements to become omnidirectional, and the complexity level is very high on the left side. While on the right side processes, the process is inherently omnidirectional and not really required any additional arrangements to make it omnidirectional. What omnidirectional is and how it works, I'll discuss about it. But this is the arrangement of these 7 processes. So the most the omnidirectionality mostly required a lot in the case of DED. It is required in material extrusion as well. It is required in powder bed fusion. It is required in wet photopolymerization. It is required in sheet lamination. It is not really required in material jetting and binder jetting. They are inherently omnidirectional, not really required. But in some scenario it may be required, but in the existing machines, not really. So at least in all these processes, this phenomena which is required, what is it and how is it really affecting, will clear many of the questions when you design your own 3D printers in future. So the omnidirectionality. The omnidirectional indicates an equal sensitivity of the process in all the directions. In the context of additive manufacturing, omnidirectionality implies invariance of material and geometric properties regardless of the travel direction. Omnidirectionality, more often than not, is a property of the setup. Okay, please remember that. Omnidirectionality is a property of the setup, means the 3D printer, the machine. It's a property of the machine. And however, few additive manufacturing processes are inherently omnidirectional, while others are made so by putting some appropriate arrangements. Fine. So let me take an example like omnidirectional antenna. Why it is omnidirectional? Because it can receive the signals from all the sides, right? It's an omnidirectional antenna. While this is a directional antenna, and you might have used it, right? Maybe in early 90s when we go to the roof and rotate this thing, because it can receive signal only from one side, not from anywhere, right? So it is depending on the direction of the process. Then this is the omnidirectional mic. It can receive a sound from all the sides. However, it may not be desirable all the time. We may need a directional mic so that you can eliminate the noises coming from other sides. Now this is an omnidirectional wheel and this is a direction wheel. Sorry. In the case of omnidirectional wheel, you can just apply the force and the wheel can go in any direction. It can rotate, it can go in this direction, it can go in this direction, in any direction on the XY plane. While the bottom wheel, if you see, it can roll over only in one direction, that is forward. And now if I use this wheel in my car, I do not really go always straight, right? I have to take turn also. So you use some additional arrangements. And what are those? Those are your steerings, right? And all those arrangements. So by using the additional arrangement, you are making this wheel omnidirectional, but it is not inherently omnidirectional. While the above one is the inherently omnidirectional. You have to just apply the force appropriately. Fine. This is a drone developed by ETS Zurich. I found this video on internet and I think they also call it as omnidirectional drone, because this drone can roll, pitch, yaw in any direction while going. While our conventional drone cannot do that, right? If it is tilting like this, it can only move back and forth. Means it can only move perpendicular to the I mean it's flat base, or in other words, along its axis only, right? And the benefit of this, having this type of a drone, is that it can really pass through tiny openings, right? Easily. So this is an omnidirectional drone. So now I hope you have some idea of what omnidirectionality is. I'm going to relate it very soon with the additive manufacturing. But at this point of time, many of you must be having, and even I'll tell you a story. When I submitted this paper first in another journal, the comment came from the editor. He was saying, no, it is nothing but the isotropy of the, or the anisotropy. It's a property of the part. We were trying to say, no, it is a property of the machine. But until one will not read the whole thing, what we are trying to say, they will really get confused. So at this point of time, and he just sent it back, and then I submitted to another journal. That's the different story. But this confusion may be with you also right now. So let me clarify this. It is important to draw distinction between isotropy and omnidirectionality. Isotropy underlies uniformity in part properties, irrespective of the part orientation and orientation or the location of the measurement. Correct? While omnidirectionality, on the other hand, is associated with the machine tool. And omnidirectional additive manufacturing platform promotes the fabrication of isotropic part. Conversely, anisotropy, which signifies non-uniformity in the part properties, can arise from several other factors also, not from only the omnidirectional or non-omnidirectional machine tool. Like it is inherently there in the additive manufacturing part because of the nature of layer by layer fabrication, thermal gradient, different type of solidification rate. The property easily changes in different directions. We know that. However, a non-omnidirectional deposition, which is often neglected by us, significantly contribute to making anisotropic parts. Also notice the definition of omnidirectionality as presented here is confined to the plane of deposition, right? Only in XY direction, like I discussed about this wheel also, not in Z direction. In a similar fashion, in our today's discussion also, we will be limited ourselves in the plane of deposition, while you know that isotropy can extend to any direction, like a third dimension also. Fine. So basically, omnidirectional, in other words, I can define is the property of machine tool which allows you to print in any direction. In any direction. Like for example, if there is a machine, powder bed machine, you print on that corner, maybe a powder bed fusion machine, print it on this corner, you print it on that corner or any corner, the properties will be same. I'm not saying the properties will be isotropic. They may be anisotropic, but same anisotropy you will get here, same anisotropy everywhere, it is same. That is what omnidirectionality is. Now let me just show you some importance of this. You may draw more importance later on, but these are some importance we could highlight. So for example, let me talk about the non-consumable electrode based DD or the warm process, like TIG based warm, okay, tungsten inert gas based wire arc additive manufacturing process. So what happened? Yeah, this is the tungsten, it creates arc, right? And it doesn't get consumed. Now from the side, there is a wire coming and it is getting inserted into the molten pool, right? If I'm moving along a trajectory which is rectangular in nature, what will happen? When I move from A to B, I will be having front feeding. When I move from B to C, I will have side feeding. And while I move C to D, I will have back feeding. And when I move D to A, I will be having again side feeding. And you can see that these feeding mechanisms look like this. Okay, I can show you the same thing by this video also. So you can notice that this is the wire coming into the molten pool. Right now it is side feeding. Now it has become front feeding. And now it has become side feeding again. And now it has become back feeding. So the issues coming here are different type of feeding mechanisms are happening, although I am moving just a very simple geometry, that is nothing but my circular geometry. Another way means how it should be. Like for example, I should be able to maintain the feeding direction all the time. It should be either front feeding, back feeding, or whatever. Or you can just rotate your bed in such a way. But that is one solution. So what happened if the process is like this? At least in the case of TIG welding, I have seen it by myself. Sometimes you will find serrations in the deposit. For example, you have set some parameters, those are feasible or absolutely perfect for front feeding conditions. Why front feeding condition? Because in front feeding, I'll just draw here and show you. This is the deposited bead. This is the deposited bead. And you are feeding wire from here. And this is your arc. And you are moving in this direction. There is no obstacle here, right? No obstacle. Hence, it will keep on depositing. But assume that the same parameter, parameter means the theta, feed angle and all, those are fixed and finding absolutely good for front feeding. Now, if I'm making this a rectangle by that, I know that at some point of time, I will, maybe in this zone, it is front feeding. When I'll come to this zone, it will be back feeding. What will happen in back feeding? I'll just redraw this diagram again here. It will look something like this. The substrate, this is the deposited bead, now this is the arc, and this is the wire. Now this is the wire, and I am keep on moving in this direction, and you are feeding wire from the back side. So what will happen? A portion of this solid wire will cut the soft molten material just got deposited, because we know that the immediately got deposited material will be quite soft, and as a result it will make a serration into it, like a dig, like we do, yeah, I mean digging into the metal, and you will see a serration like this as you are seeing in this diagram. And this is quite common, I have seen it many times. Also, if you are using, for example, different kind of feeding and depositing in the same platform, you will face an offset, because the wire doesn't melt at the center. Sometimes it depends on the wire feed speed. Not today is not scope, but there are many analytical models where you can identify where the droplets is going to be melted. So for example, it is melting at this location, not at the center. Now what will happen if you are doing the back feeding and you are doing the front feeding? It will be definitely in line with this axis, but if it is changing the axis, you see that there will be some offset. This particular path is the path what we are giving through the CNC machine, but as a result the material will be deposited on this blue line. There will be offset, the whole thing will get offset. And if you're really talking about micro deposition, not really possible. You will be having many defects in that case. Also, I have discussed a little bit this phenomena yesterday. When the wire is coming from one side, right, it will absorb some of the energy from the arc, and the energy available on the substrate at this zone will be less. As a result, you will have more penetration on the other side where there is no wire, and you will have less penetration on one side where there is wire coming. And always you will find a bead like this. And right, it is obvious, it's very obvious. Now, if you keep on, do not really rotate it, what will happen when the feeding mechanism will change? Earlier you were getting the on this error on the left side, I mean the less penetration on the left side. Now you will get the less penetration on the right side. So there are issues. If there are issues, and this is only I discuss about the DED, the issues are in many places, and I'll discuss when I'll discuss about each and every process in detail. We have to first convince others and you also today that whatever we are telling about the omnidirectionality follows a mathematical rule, and it remains consistent when you apply it to any additive manufacturing machine. Then only people will appreciate our hypothesis, right? So let me define. The directional sensitivity in additive manufacturing process basically arises from the inconsistency between the spatial orientation of three vectors relative to each other. And those three vectors are namely the source of fusion, VS, source of fusion like arc, laser, electron beam, whatever, and the direction it is coming from. Fine. The direction of feedstock delivery, along which vector you are depositing or adding the material, right? And yeah, any doubt? Okay, fine. Okay. And the direction of feedstock delivery along which we feed the material, and finally the vector corresponding to the travel direction. So these three vectors, VS, VF and VD. Now these three vectors terms as orientation vectors. So the condition for inherent omnidirectionality, if the process is inherently omnidirectional, this condition has to be satisfied, what is written here mathematically, that Vs, the source of fusion vector, should be always parallel to the fusion vector, the feedstock delivery vector, and the direction of the deposition direction, or the in the direction you are depositing, should be perpendicular to the feedstock delivery. And also the deposition vector should be perpendicular to the source of fusion. Then only your process will be inherently omnidirectional, otherwise not. Fine. Let me just consider one case. This is a case of MIG welding based process, MIG. What happened in the case of MIG welding? The wire comes vertically. For example, the heat source or the arc is also generated by the wire itself, right? The wire itself generates arc. Hence, the direction of arc is vertically downward, and also the wire feeding direction is also parallel to that. Correct. In that case, I can say Vs is parallel to Vf. Fine. And we are moving along a path. The path is shown here in the blue color. Anywhere, if I take a vector, that will be called as vector Vd. And you see that Vd is always perpendicular to Vf and it is perpendicular to Vs, right? If that condition is satisfied in the case of MIG welding, as I am restricting myself only in the planar deposition today, there will be no issue at all. Process is inherently omnidirectional. In a very similar fashion, pre-placed feedstock type system means the feedstock is not having any velocity at all. You are spreading a layer of powder in the beginning itself. In that case, what will happen? The Vf will be 0, right? It is not moving at all. And assume that there is a laser coming from the vertical and you are going in this direction, Vd direction. If the laser is coming vertical and you are moving on a plane and always the angle is maintained 90 degree, then of course process will be omnidirectional. But if it is tilting, it won't be. And that is the major reason. And so you got the examples of omnidirectional systems. Now let me give you an example of non-omnidirectional nature, how it arises. Sometimes what happened, this source of fusion or source of energy is separated from the feedstock delivery, and it is quite obvious in the case of plasma, laser, and EB, or even in TIG. You generate the source of energy or arc by a different mean, and then you feed the wire or powder in it, right? And then you move in direction. When you feed the wire into it, you feed it at an angle. Now you see there is an issue now. Assume that this angle is 90 degree. It is always perpendicular. Now if I'm moving in this direction, the angle between Vf and Vd is something. It is something, for example, this one. Okay. Now suddenly if my direction of motion is changed and I'm just going in backward direction, the angle will change. Now this will be the new angle. So what is happening? The position of Vs, Vf and Vd is not consistent. Hence process is not omnidirectional. Let me just consider another example where maybe the powder feedstock is at 0, it is at rest, it is not moving, but you may deflect your laser beam away from center. In that case, what will happen? There will be an angle between Vd and Vs. Earlier it was 90 degree, now this angle has changed and it is represented here by phi. You move in another direction, this angle will again change. Hence, the angle between Vs and Vd is not consistent. If the angle is not consistent throughout the process, when you move in anywhere on the machine, process is not omnidirectional. So I hope the definition of the omnidirectional is clear. Now I'll extend this towards each and every additive manufacturing process. So let us first consider omnidirectionality in DED, directed energy deposition. So for the directed energy deposition based additive manufacturing processes, the feedstock is fed instantaneously along vector Vf into the molten pool created by the fusion source. Hence, the relative position of vectors Vs, Vf and Vd, Vs, Vf and Vd may vary when follow a non-linear trajectory in the XY plane. Of course. Now in the case of metal inert gas cladding, MIG cladding based process, the feedstock enters the molten pool coaxially. Meaning to say, I have already explained this, it is given here again. This is the wire, right? This is the MIG welding wire. This wire itself is creating the arc, right? And if the wire itself is creating arc, hence the vector Vs means vector corresponding to the source of energy and vector corresponding to the feeding of wire will be coaxial. And you are moving on the substrate in the direction Vd. Now you go in any direction, in this 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 direction, anywhere you go, the angle or the orientation between Vs, Vf and Vd will be always consistent, hence no issue at all. Fine. This effectively yields a uniform deposition condition regardless of the contour trajectory. Whatever contour you are moving, it is fine. However, the condition is not same for TIG welding or plasma or laser or electron beam. In such cladding processes, the relative position between Vf and Vd may vary because of variation in the travel direction. Therefore, the AM processes are not inherently omnidirectional. Let me give you an example. This is the tungsten, right? It doesn't get consumed, it creates arc. Hence, vertical is the direction of the fusion source vector, Vs. Now you are feeding wire at an angle from this, maybe at an angle theta, assume that. This angle is Vf. And you are moving in a direction Vd, that is the deposition direction. Now this angle theta, what you have considered here, may and it will have some angle between this and this also. So let me define that by phi. Now this angle phi may change. How it can change? For example, you are suddenly moving in another direction. Assume that you are going just in opposite direction. I'm just considering opposite direction. So this phi, which was phi earlier, now will become 180 degree minus phi, correct? Now this will be the angle between this. Hence the angle between Vf and Vd has changed. And this is nothing but the front feeding and back feeding, if you recall. But we just defined it mathematically so that it makes sense. Therefore, I'll tell you here, whenever any one of us, started working on WAM, we like to use MIG welding. Nothing at all required. Get a gun, mount on a CNC machine, mount on a robot, start investigating. Issues will arise, of course, but not really in the system level. You will be having your system immediately ready. So if you want to start your research or some investigation on WAM, I'll recommend you to go with MIG welding. And the reason is in front of you. No auxiliary arrangements are required. Now, if you are going with TIG, you will end up making only lines. And you will read in many papers. You go and read papers related to TIG. Very few people have really made very complicated geometries until unless they do not do some auxiliary arrangements with the wire feeding direction. Otherwise, wire is single line is fine. You can deposit in only one direction. And of course, you can do the characterization. Of course, it is very useful as well. But you can't really make something useful until you will not have the omnidirectional process. So the point is, DED processes are except the MIG welding. Now you can replace this tungsten with the laser also. And you can replace it with electron beam. You can replace it with plasma. So in other words, I can say only MIG welding is the one in which Vs and Vf are coaxial and perpendicular to Vd and hence inherently omnidirectional. But other than MIG, there is no DED process based on the other four processes inherently omnidirectional. We have to make. So let us talk about them in detail. How to achieve omnidirectionality in DED. We proposed four possible methods. One is coaxial feedstock and fusion source, meaning to say Vf and Vs both are coaxial. This is Vs, right? This is Vs. They both are coaxial and you are moving perpendicular. In XY plane. Hence, this vector will remain perpendicular. But you know that it is only possible with MIG. But it is a solution. If you can do that with TIG, great. It's not possible, but yeah. Although, now another method is coaxial fusion source surrounded by feedstock. Meaning to say, the fusion source will be coaxial. It is coming from the center. This is the fusion source. And its vector is Vs. And it is surrounded like a cone, okay, like a cone by the vector Vf. And you are moving now in any direction Vd on the bottom. Now you just tell me, take a picture. Assume that you are taking pictures. Vd is in this direction right now. Assume that it is in this direction when you took a picture. Assume that you took another picture and Vd looks like this. And another picture you took and Vd looks like this. So at any point of time, you can see the scenario is same. The angle between Vd and Vs is same. It is always perpendicular, 90 degree. And the angle between the cone of Vf, it is cone. It is symmetric everywhere. The scenario is same, right? You are moving in this direction. This much material will be in the front. This much material will be in the back. Now you move in direction. Same condition. This much material in front. This much in the back. Angle between Vd, Vf, and Vs is same now. You move in any direction. Vf is having same angle, right? It is at cone. At conical angle. Hence, Vd, Vf, and Vs are consistent. We have to do this mechanism, but imagine that it will be difficult to do with wire. How can I make a cone of wire? Wire is not in discrete forms. I have a finite volume for the wire. So it will be difficult for that, but I'll tell you the approximation later on. Another way is you feed the wire or powder centrally. I mean coaxial feedstock. VF is coming from the center, and make the heat source surrounding it, like surrounded by the feedstock or fusion source, that is VS. Okay, this orange color is VS. Now it is very similar to this one, but instead of making a cone of powder or the raw material, here it is the cone of the fusion source. Hence now you move in any direction, VD, VF and VS are consistent. You go here, here, anywhere, right? Move in any direction. The fourth one is dynamically adjusting orienting vector, the cheapest and the easiest one. Now the angle between, the issue is the angle between VD and VF, right? This angle, the theta. VS is always perpendicular to VF, and also the angle between VS and VD is constant. What I can do, I can rotate my wire feeder, why not? So for example, you are moving on this trajectory, this black color is the trajectory. Just look at it very, very carefully. Right now the tangent to this point is in this direction and it is making an angle theta. Now I move to another position and now the tangent to this point is VT, and now you are moving in this direction. Okay, read this VT as VD, huh? And now you are moving in this direction. What you need to do, as this angle has increased, you need to rotate your feedstock and bring it to the position, hence the angle remains maintained. And this I will call it as dynamically adjusting orientation vectors, so that at any point of time the angle between VF and VD will be theta, the angle between VF and VS will be something, maybe phi, and the angle between VD and VF, VS and VD, angle between the fusion source and the deposition direction will be always 90 degree. But I have to make these arrangements. Now I'll show you in each and every additive manufacturing process I have found patent, not filed now. People are doing it from 1988 or very, very old papers. But yeah, there was no well-defined definition, but based on the requirement we were doing. Let us talk about first the TIG or plasma cladding. So method 2, the method number 2, this one, the coaxial fusion source surrounded by feedstock, and method 3, coaxial feedstock and surrounded by fusion source, and method 4, that is dynamically adjusting feedstock, are applicable for TIG or plasma cladding. Let us discuss first method 2. Method 2 says to make it omnidirectional, you should have coaxial fusion source, means center should be the arc. In the case of TIG, we are talking about TIG or plasma. So this is the tungsten and it is having a arc at the center, right? This is the arc. This arc is creating molten pool and you are feeding wire in it, right? From all the sides. So I cannot really make a real life cone, right, by wire, but I can use maybe n number of wires, maybe 30 wires, and that I will feel approximately from all the sides towards the molten pool. That can make some kind of a cone also, but 30 may be a good, very large number. So why don't we reduce it to the minimum possible number? So minimum possible is 3 wires. So you feed 3 wires from 3 sides. They are 120 degree apart, and at the molten pool they will look like merging from all 3 sides. And now you move in any direction. You move in this direction, in this direction. You move in any direction. What will happen? The scenario will be same. Okay, this is the approximation part. It is not really a very good solution for omnidirectionality, but approximately the angle between VS, VF and VD will remain consistent. The third one is the coaxial feedstock surrounded by fusion source. It is possible. I have found these patents. The reference is not given here, but because I made this diagram. So if you want, you can read the paper. The reference must be given there. The patent was found for TIG welding and plasma welding process where the electrode is hollow. If the electrode is hollow, what you can see in the case of TIG welding, this is the TIG welding, the tungsten is outside, but it is in the hollow form. Okay, what you are seeing here. And then one can feed wire from the center. Now this hollow electrode creates arc, a hollow arc basically, which looks like this, right, like a cone, and merged at the molten pool. Now in the molten pool created here, one can feed the wire and wire get melted into the molten pool. Now, of course, it's a cone of energy source. Now Vs, Vf and Vd, the vector is consistent, move in any direction. Right? Now one can say with confidence that it is the omnidirectional process. Similar way, we have found a literature on plasma as well, where the conical plasma was generated. The electrode inside was hollow, and that creates a conical plasma. In that conical plasma, that further creates the molten pool. In that we feed the wire, and that wire get melted onto the substrate and deposit the material. Here you can see Vs, again the envelope created by the plasma welding. Vf and Vd are consistent, very similar to TIG. There is no very big difference between TIG and plasma. The only difference is additional gas is supplied in the case of plasma, and tungsten is a little bit inside. The additional gas get ionized, and those ionized gas comes out in the form of plasma instead of the tungsten projected outside. The fourth solution, which is I have seen in the additive manufacturing more popularly, is the dynamically adjusting feedstock or deposition direction. So there are two ways. As per this method, omnidirectionality can be achieved by maintaining a constant relative position between the feedstock delivery vector Vf and the travel vector Vd. Look at this system. This is the arc generated. This is the wire fitted. Now let me draw the vector diagram of the same. This is the Vs, the source of the energy, that is vertical. Then this is the direction in which I am feeding the wire, and this is the direction I am moving. And this angle will keep on changing. Hence, what will happen? This angle is fixed because I have attached it with a rigid system. You see this steel gray color thing? It is rigid. So this angle is fixed. Maybe it is phi. But this angle will keep on changing as Vd is changing. So what I can do, assume this case, this one, instead of moving the head, if I just rotate this substrate only, what will happen? That the direction of motion will also maintain. Fine, but this is for circular object. It will definitely work with the a random contour also. And I did that. I tried it. So the thing is, this particular one is called as dynamically orienting the workpiece. You are dynamically orienting the workpiece in such a way that the angle between Vf and Vd is always consistent. It never changes. Correct? Now, next is omnidirectionality through dynamically orienting the feedstock itself. So why don't we just make this arrangement on the bearing in such a way that this angle remain maintained? This should not change, but this should rotate about it. And what will happen if this will rotate? You will have the provision of changing the angle between Vd and Vf easily. So if you are moving in this direction and you are going to move in a circular trajectory, this wire feeder will also move along a circular trajectory, and hence all the time the angle between Vd and Vf will be maintained. There won't be any much issues, right? Let me just consider now, and let me just show you the videos. The solution here you will see is dynamically adjusting the substrate. I'm going to make this circle. You see that this rotary table is rotating, and all the time it is front feeding now. And that is what we wanted. But the issue is you need an additional axis, right? In that case, XYZ is on the top, but on the bottom you need additional axis. So 4-axis system is required minimum, right? Or you can rotate your wire feeder like you see here. It is always maintaining a side feeding. This system was also developed. So we developed these two systems in IIT Bombay. So this is dynamically orienting the feedstock. And when we deposit and found, we really got very good results as compared to the conventional TIG welding. So that was about the TIG. Now let us come to the laser cladding. We have a benefit here. When I use laser, I can use powder as raw stock material. Not only wire is always required as a raw stock material. So generally, for the wire form of feedstock, the method of its feeding into molten pool is similar to the one discussed for TIG and plasma. However, when we use powder as feedstock, special designs or nozzles are available. So let us apply method 2, 3, and 4 here for laser cladding system, omnidirectional laser cladding system. So method 2 says the coaxial fusion source surrounded by the feedstock means from the center you will have the laser, right? I'm sorry. Let me take a different color this time. Yeah. So from the center, this is the laser coming, right? Now I have an annular nozzle. This is the annular nozzle. I am feeding powder into this annular nozzle in such a way that it forms an angular form of envelope around the molten pool and hence get converged. So the good part is the laser is creating the melt pool and you are feeding the material now in a conical form. So if I draw the vector diagram of the same, it will look something like this. You have Vs that is vertical, you have Vf that is in the conical form, and you are moving in the Vd direction of deposition. And now the angle between Vd, Vf and Vs is always same, right? Hence the process is omnidirectional. Of course, there are issues with this type of nozzle. We have discussed it yesterday, because when you tilt such nozzles, the direction of powder become more at one end and another band. Also, FGMs are not really very easily possible here. So 3 nozzle systems also can be used. That is why when I was discussing yesterday, I always say minimum 3 nozzles are preferred by in all the systems. Then you increase, like I already said, you use 30, 40, 50, that doesn't matter. But minimum 3 is required, because 3 can approximate a cone. And the 3 are at 120-degree apart. They will form an approximate cone, and that will look like here shown in the VF. VS and VD, now in this case also, they are approximately but consistent throughout the process, and the process becomes omnidirectional again. Fine, but it is an approximation. Increase the number, catchment efficiency will increase. I mean, many issues will resolve, right? Process will become more symmetric if you use more number of the channels. But the issue is, of course, you have to control more controllers are required and all. The third method is the coaxial feedstock surrounded by fusion source. But now the issue here is you need to have the expertise in laser. Achieving omnidirectionality through central powder feed and annular beam nozzle has been explored by quite a few research, even though such a setup has shown to possess high power catchment efficiency. It is generally not preferred due to the involvement of complex optics, and system become very, very bulky. I'll tell you a few names. The system you are seeing here, it is annular beam thing that is already developed by Precitech. It's a US based company, I guess. Yeah, Precitech. But instead of powder, they feed wire from the center. And now the beam is coming in an annular form, right? So it's a cone of the laser, and hence it is written here as VS. It's a cone of laser. Then from the center, you are feeding the wire or powder. And now you move in any direction. That is your VD. Hence the angle between VD, VF and VS is consistent, and the process is omnidirectional. How to convert a solid beam into the annular beam? There are many optics required in between, like prism, hexagon mirrors and all. For details of this, you can refer to any of the journal where they have used the head of Precitech by USA, I guess. Then next is this one, where a single solid beam, it is an approximation now, but this is the best one. But the system become very bulky. Optics is quite big in this case. While approximation of this is you use a laser beam, passes through the splitter like prism, is to split the laser light into 2 or 3, and then further converge it to a point. So now in that case, you will have 3 laser beams. Like I already mentioned yesterday, I have read in some papers, they just mounted 3 nozzles also. Just mounted 3 nozzles. But the better representation is given here. So it's an approximation. It will form a cone of fusion source, that is Vs, and the vector corresponding to that. Vf is the vector corresponding to the powder or the wire. And now you move in any direction. Angle between Vd, Vf, and Vs will remain consistent. Hence the process is omnidirectional. This is a system developed by Fraunhofer for wire-based system. You see here, wire is coming from the center and 3 laser beam from 3 sides. There is no other reason than the omnidirectionality here. They call it as coaxial nozzle. And then of course you mill it and continue that about the process. We are not going to discuss about that today. and then again you deposit. Center is the wire. 3 laser beams are creating a molten pool and then feeding the wire. You are feeding the wire from the center. Anyway, so the fourth method is dynamically adjusting the feedstock delivery or deposition direction. In this method, as discussed previously, a consistent orientation between the feedstock delivery vector VF and the deposition or the travel direction VD has to be maintained during the build. This method requires dynamic or on the fly adjustment of either the material feed or the substrate direction to achieve the omnidirectionality. It has been noted, even though such a setup is feasible for wire as a feedstock, its use for powder is not really, I have not seen any system where dynamically they are changing the direction for powder. Why? Because it can be observed that the powder feedstock is suspended in a stream of inert gas, right? And if you rapidly change the direction or rapidly changing the position of the laser head, it could lead to decrease the catchment efficiency. This is because the rapid change in the feedstock orientation are more likely to disrupt the powder flow characteristics and hence rise to a spray-like pattern rather than converging one. May not be a good one, right? So, but if it is for wire, yes, people used to do that only. I'll just, before moving to electron beam, I'd like to mention here one thing. When people use laser wire, lot of such development you can see in Cranfield University. They usually use the 6th axis of the robot, that is the Z axis, which is a rotary axis about its arm, that they utilize to feed the wire and adjust its orientation with respect to the deposition direction. They keep on rotating it, right? And they rotate it appropriately so that all the time front feeding can remain maintained. So now you know the reason why they rotate. Electron beam cladding. As there is a vacuum environment of approximately 4 to the power 10 to the power minus 4 torr is required for successful melting processing using electron beams. Since most of the powder stock handling system are using pneumatic methods, wire are popularly used as a feedstock in EB. In order to achieve omnidirectionality in EB system, method 2, 3, and 4 from the previous discussion can be implemented here. Method 2, which was the coaxial fusion source surrounded by the feedstock, due to the pneumatic involvement in the powder feed, the powder is not used, so there is no possibility of making cone. And only thing you can do EB system with using the multiple wires, and you know the reason, because if you use the multiple wire, those are 120 degree apart, and you are feeding simultaneously them into the molten pool, it will approximately make a cone, and in that cone you are due to the cone of the VF, the angle between VF, VS, and VD will remain maintained. The second method, the third method could be coaxial feedstock surrounded by fusion source. Meaning to say, in that case, you will have a conical form of electron beam also, and it is possible. Even there is a system, I forgot the name. Okay, if I'll be able to recall, I'll tell you. They used to use hollow cathode. So this is the cathode, right? And there's a potential difference between the cathode and the substrate. It emits the electron, right? These electrons move towards the substrate. As this is a hollow cathode, the electron beam will be also hollow. And as it is a hollow cathode, the hollow electron beam, you can feed wire in the center. And as a result, you will have a hollow, this conical shape. If I draw the vector diagram of the same, conical shape of the energy beam or the energy source, hence Vs is conical, Vf is vertical, Vd is in any direction, hence the angle between Vf, Vs, and Vd is consistent throughout the process. Already they developed and they are using it. I think X beam is the company. Another one is another idea which is still under development. Sorry. Okay. So another idea which is still under development, in which 3 electron beams are used. One electron beam gun 2 and electron beam gun 2. Electron beams can move with a very high speed because of the involvement of magnetic coil. We know that there is no physical thing there to move, only the current you have to change, and it will deflect the electron beam in different directions very fast. You can oscillate each and every beam in this manner that it creates 1/3 of the circle. Okay, if there are 3 beams, they can rotate like this and create 1/3 of each circle, and then it will create a molten pool, and in that molten pool you feed the wire. right? So approximately, if you see, it will look like this. If I draw the vector diagram of the same, Vs is in the cone, but as by the 3 guns, and from the center you have enough space to even feed a wire, and then you move in any direction in Vd. Hence, the angle between Vs, Vf, and Vd is same. Or you can dynamically adjust the feed stroke deposition direction. Now there is a video by Siaki, so you will be able to see that in the beginning itself. So I'll rerun this. They used to rotate the substrate. They have a rotary axis on the substrate, and in our words now we can say that they are using dynamically adjusting the deposition direction by rotating the substrate appropriately by the 4th axis. So you just see this here in the beginning itself. The substrate is rotating. You see that, even though it is just making a rectangle thing, right? Again, I'm playing. The substrate is rotating. It is rotating just because of that only. The wire is feeding from the side and the rotary axis rotates it. They will again deposit. You see that this is the rotary axis, and it was just required to maintain the front feeding always. Hence, the Siaki uses a rotary axis basically to appropriately rotate and deposit the material, and hence to maintain the omnidirectionality. Now let us discuss the omnidirectionality in material extrusion. So in the case of material extrusion based additive manufacturing processes, typically identified by nozzle through which the material under pressure is forced out and deposited on the print bed. Fused deposition modeling, FDM, is the most common extrusion based additive manufacturing technology for polymer and plastic. FDM is generally assumed to be omnidirectional in nature, as the material is extruded through a circular orifice, resulting in uniform track dimensions. So in that case, there is no issue. But in the case of material extrusion in the field of construction, they have a unique challenge. Because unlike polymer FDM, square outlet nozzles are preferred over circular ones in the case of construction industry, if you closely observe sometime. Why so? Because this assures in the stacking of the layers and prevent the porosity. I'll just show you here. If you deposit the circular nozzle, what it will end up? It will end up like this, right? And you will have some porosities in between. Because unlike in the case of wire-based system, where they get merged after some time due to the high temperature, there is no temperature difference here, and just a ceramic slurry. They prefer to have rectangular nozzles so that the stacking can be proper. There are two reasons: stacking and the voids. Okay, so what happens? As the stacking is much better in that case, and you are using rectangular nozzles, when you move in different directions, you get different dimensions. So this figure A below, for rectangular nozzle, it is showing when it is, and assume that the dimension of nozzle is this width is, assume that it is B, and this width is this side is A, and diagonal is C. Now if you are moving back and forth in this direction, your deposited bead width will be A. If you move back and forth in opposite direction or in perpendicular direction, your bead width will be B, and if you print diagonally, it will be C. In between, it will be something else. So the process is not omnidirectional. Let us apply our definition here. If you move in any direction, it is depending. In which direction you are moving, you are getting different results, not the same results. Hence, the process is not omnidirectional. So we have to do something. Another issue here also, that if you take a turn, for example, you are depositing like this and then you are taking a turn, there will be a twist here, right? From this much width, it is changing to another width. So there will be a twist at the corners like this. So how can we really resolve this issue? It is possible by rotating. You remember our 4 methods? Out of that, here I'm applying method number 4, that is dynamically adjusting the feedstock delivery. Similar to TIG or plasma, in this method, the deposition head is held vertical and stationary while the substrate orients itself such that a geometrically uniform track is deposited. Alternatively, the deposition head can be oriented. You see this one, this diagram on the left side. When you are moving, this is in line with that, right? This is in line, this is in line. So each time you have to rotate it, right? This is the local coordinate system of the nozzle, and you see that with respect to the fixed coordinate system, its position is always changing. right? Now just observe this video. Here you can see this nozzle is rotating, right? It is rotating because of that only. To maintain the process omnidirectional, right? Keeps on depositing and finish it. Anyway, now we'll move to, now you know that why the rotating head is used to make the process omnidirectional. Now we'll discuss omnidirectionality in wet photopolymerization. What happened in wet photopolymerization? Most of the stereolithography systems uses a galvanometer to deflect the incoming laser beam onto the photopolymer laser bed. So what is galvanometer? Galvanometer is nothing but a mirror on which when a laser beam falls, it deflected back on the bed. If it is perpendicular to the bed deflecting, you will get nothing but a circular spot, right? That won't be any issue at all. But if I deflect it away, and in that case, and this is my bed, what will happen? The circular beam, the cross section which we will get on the bed will be not circular, it will be elliptical. And I'll tell you, an inclination of 45 degree reduces the power density by 30% and increase interaction time by 40% at original travel speed. So this beam distortion inadvertently change the processing parameters during the fabrication, thus producing non-homogeneous part build. You build part at this location, you build part at this location, you build part at this location, will not be having the same property. Maybe anisotropy, but not same anisotropy. So given the fact galvanometer are used to scan the layer geometry in most SLA system, beam correction is essential to make the process omnidirectional. Now, even if you discuss it with respect to the vectors, let me discuss, you will appreciate it immediately. Because if this is the liquid bed, right? Hence, liquid is not moving, your VF is 0. Fine, VF is 0. So there is no feed for the material. But how the laser beam is coming? In one condition, it is here, and assume that you are moving in this direction. This is your VD. The angle between the laser and VD is 90 degree. No issue. That means VS and VD is 90 degree in case 1. Right? Now let me consider case 2. And the case 2 is, I am saying that the laser beam is deflected somewhere else due to the change in the position of this mirror, right? Now this is my new position of the laser. Again, I am going in the same direction. VD is same. Assume that. Now the angle between VD and VS is changed. It is no longer 90 degree. And VS is not really perpendicular now to VD. That means the process is not omnidirectional. Vectors are not consistent. We have to do something. So to ensure that omnidirectionality in wet photopolymerization to large extent rely on the beam corrections. Hence, in succession to our previous discussion, those 4 methods may not work here. We will propose to you the fifth method, that is called as fusion source beam correction for the GSS system, galvanometric scanning systems. Okay. So why so? Let me just explain it. The galvanometer restrict the motion of workpiece in XY plane, and the laser head, unlike the flying optics, I'll discuss about what is flying optics. High scanning speed up to 1000 mm per minute can be obtained. But F theta lenses are essential component for galvanometric systems, and they ensure a flat scanning field, a small spot diameter at the focal plane, and circular and uniform spot shape anywhere in the scan field. So what is it? If you do not have F theta lens, assume that there is no F theta lens, right? So what will happen? The laser beam will have the focal point in a circle trajectory, right? Meaning to say, its diameter, if it is D, it is here D, then it will be D in this location. And this is nothing but the equal to the focal length, right? So focal plane will be this circle. Now I can tell you, if you want to make maybe you can come up with some idea. Instead of having a flat bed, you can have a circular bed, and then fine, then no issues. Then you can deflect your beam from one end to another bed. One more issue, I'll tell you one more very important thing here. You can note down why SLA printers are so tall. Earlier they were so tall because if you increase this height of the SLA, this portion become more flat, right? You know that if the radius of the circle increases, bottom portion become more flat. Hence, they get less irritation, less bad results for the beam correction, right? Now, what is the solution? The solution is using the f theta lens. If f theta lens is used, it just project the light downward at whatever angle it is falling. So the focal length is depending on the theta. Theta means the angle it is incidenting on it. And hence it is always in the flat line. It is always on the flat line. And it is maintained. That is called as f theta lens. Fine. And this arrangement is required. You know that why? To maintain the process omnidirectional. Why it is omnidirectional now? Because now light is falling vertically at any location. That means you move it in this direction or in that direction, anywhere, the angle between Vs and Vd will be always 90 degree. And that is what we said in the beginning. If the angle between Vs and Vd is 90 degree and Vf is of course 0, process is omnidirectional now. Another easy solution is, why don't we just move our optics instead of deflecting it by the mirrors? Of course, deflecting it by mirrors was important because we get very high scanning speed. But there are few systems I have found on YouTube and other sources. Unlike galvanometers, which uses mirror to deflect the energy beam, in flying optics means your optics is flying, means it is moving on XY bed. Like for example, here there is a motor attached with a lead screw. It is moving in X direction, it is moving in Y direction. Hence, your laser itself, beam is moving. And if it is moving, anyway, it will always remain perpendicular to the bed. And hence, VD, VS and VF is 0, means they are consistent, and hence process is omnidirectional. So this is the fifth method, that has the fusion source beam correction through flying optics. But you have to make a compromisation on the speed. You see this one? This is the bed of the photopolymer liquid. And this red dot is the laser beam. Now this laser beam is moving. And the whole optics is moving, right? Maybe some mirrors are mounted on that. They are moving. And hence, it will always perpendicular. You will have no issues. But you will go with a very less speed. If you look at a SLA process, sometime you won't be able to identify where the beam is. It moves with such a high speed, right? Another solution is lying with the DMD, digital mirror devices. What they do, in the case of digital light processing based system, a digital mirror device is used to selectively project the UV light on the photocurable resin for part fabrication. Alternatively, several mask-based techniques are also available, right? You might have seen in the solid ground curing and all. What happened? The light is going perpendicular, like in your projectors, right? Conventional projector. Wherever it is required, the light is deflected. Wherever it's not required, the mirror tilts itself in another direction, right? So I'm not going into the detail in this lecture for this, how it works, but they just make sure that the light, perpendicular light, which was already coming, is directed or not directed. Fine. So this is called as irradiating a layer at a single time instead of scanning it with a single beam. Now omnidirectionality in sheet lamination. So sheet lamination is an additive manufacturing process that employs pre-placed feed stock. Pre-placed feed stock means, let me write here, VF is 0. Okay, pre-placed. You are placing it and then not moving it. Shaping the feed stock corresponding to a layer geometry can carried out by multiple means. Like for example, in the case of paper feed stock, layer geometry is carved either by a mechanical knife or a laser. And in the case of metal, hand milling cutter is used. So this is an example of FSW based layer additive manufacturing, right? We have also tried here. I think I have a workpiece here. I'll show in the end. So this FSW tool is moving along a path, right? As this is the source of energy. So let me say Vs is vertical. Vs is coming vertical. And this is the deposition direction. And tool is always perpendicular. You are not going to tilt the tool. Hence Vs and Vd are perpendicular. The process is omnidirectional. And that is true with the paper loam also. But I already mentioned yesterday, if there is a sheet-based process, machining has to be done. The cutting operation is inherently there. The process is always hybrid. Otherwise, it won't work. You will end up making cuboid, not real life structures. So what you can do, you can cut the material. And usually the material is subtracted by a cutting tool, right? The cutting can be done by laser or it can be done by hand milling tool or by knife. So the source of fusion is perpendicular. Process is in omnidirectional for joining, but process may not be omnidirectional for cutting. Why? Let me just tell you. Let us check for the inherently for metal deposition. Metal deposition is inherently omnidirectional. Let us check for cutting. In the case of polymer, similar to concrete printing, an additional constraint need to be imposed to ensure omnidirectionality. Fine. Apart from polymer, other than feedstock type, that can be considered under a similar perspective, like our paper, cardboard, matboard, wood, foam, leather, and all. Implementing this additional constraint requires special arrangement and thus make the process inherently omnidirectional later on. In addition to this, method number 4 can be used. Now, I'll just explain. For example, you have a knife. You are cutting this paper, and there are few additive manufacturing processes like Kira's loam. They uses knife to cut the paper. Now, if I'm moving my knife along a trajectory, right? I'm moving my knife along this trajectory. I have to rotate my blade, right? You just keep the blade in your hand and think about it. Blade is not an omnidirectional cutting tool. And milling cutter is. If you have a rotating and milling cutter, move it in any direction. It will cut back and forth in X direction. By any direction you move, it will cut. Knife cannot cut. Knife cut only in one direction. If you want to cut in another direction, you have to rotate it. Rotating it means we already discussed dynamically adjusting cutting edge orientation. Now, as it's not deposition, we are giving a name, dynamically adjusting cutting edge. Or you rotate your substrate, but fine, let me rotate my knife only here and carve it. If you are using laser, that also issue, because if laser is used, galvanometer will be used, and if you are deflecting it away, beam correction is required. Hence, there are two options if you are using laser beam. Either you use flying optics, means you move the entire beam at that location, or you use F theta lenses, right, to make the process omnidirectional. Then omnidirectionality in powder bed fusion. In several aspects, like powder bed fusion is very, very similar to wet photopolymer. Here, there was a pre-placed liquid. Here it is a pre-placed powder. VF is 0. But the VS and VD may change because the laser is deflected by the galvanometer. Hence, in that laser also, they used to use the F theta lenses. But unfortunately, other options available for wet photopolymerization like do not work here. But you may think, why not? Like irradiating the entire layer at a time. It is not available for powder bed fusion because the laser power is quite high. We go up to 600 watt. May not be using that tiny mirror and deflecting and all. May not be feasible here. While in that case, the laser power is hardly in milliwatts, right? We know that. So that is why those method irradiating laser doesn't work. Only two method works here. Either you use F theta lens or you use flying optics, nothing else. So it is shown here. So I'll just quickly finish it. You see this F theta lens. The laser is falling at an angle, and then you're deflecting always perpendicular. Always perpendicular. If it is not perpendicular, it will not work. If it is perpendicular, fine. Now imagine how big this lens could be. There is a limit for that, right? Yes, if you can invent a 2-meter big lens, then yes, you can have a very big, very large area, maybe machine also. But due to the limitation of F theta lens size, we can't really correct the beam shape up to a certain limit. Hence, we can't deflect beyond a certain limit on the lens. Therefore, that is the reason today you know that why these systems are limited to 250 by 250. And if you go say that I want a bigger machine, then they will say that, okay, then you have to use multiple lasers. And why multiple laser? This is the reason. Because we can't make the process omnidirectional for a single laser beyond 250 by 250. Then the last one is use the flying optics. Of course, this is the crude and the best way, and not really unrealistic. I think I have seen by it's a Chinese machine, but I think Exact Metal or something. There they use the flying optics for the powder bed fusion. They move the entire laser beam in XY direction from the top and scan the bottom layer. Now you have whatever big you want, maybe from this end to that end in kilometers, whatever. Okay, you can really deposit. I'm not talking about the metallurgical aspects and all, but from the point of view of omnidirectionality, it will work. No issues will come from the machine tool side. If you use the flying optics, yes, it will be slow. It will be very, very slow as compared to the galvanometer, because in galvanometer, the moving mass is very, very low inertia, very less mass is there. But here you are moving the whole thing. You can't really give a very good acceleration to the flying optics. Also, optics may break, and you can't move the bed, because if you move the bed, your powder will be disturbed. So the only option is to move the optics with slow speed. Omnidirectionality in material jetting process is inherently omnidirectional. Because why? Because the, for example, how it works, just let me tell you. Binder jet and material jet both. So first let me discuss the material jet. The material is injected like in your printer from a nozzle, right? And each and every nozzle just perpendicularly drop the material, right? Just perpendicularly. There are several nozzles, right? They do not deposit the material at any angle. They always deposit the material only vertically downward. Fine. So this is the direction of VF, right? Material coming direction. You are moving always in towards me in that case, है that will be your deposition direction, and it will be perpendicular to VD. And what is the source of energy? Energy source is also always parallel, because that is only generating the droplets, right? So VS is parallel to VF, and VD is perpendicular to VD. We have already said in my first slide that if that is the condition, process is omnidirectional. Now, if it should not happen that one is standing here and then injecting the material at an angle here, then there will be issue. Then the process may not be omnidirectional, because your VF and VD, the deposition direction or the motion, is not perpendicular, and the angle may change. Process is not consistent. Then you may need to use some mechanism to inject it appropriately. An interesting case of cold spray in practical, in the particle, a particle can impact the substrate normally, and that is normal to the substrate, or at an arbitrary angle, which also would result in decrease the powder catchment efficiency. In other words, more tightly the process added to the omnidirectionality, it will be more efficient. So always when you design the system, think about this omnidirectionality. You will not be able to see its benefit disadvantages now, but if you think about it, you can be increase the efficiency of your process. Then binder jetting, similar to material jetting. In the case of binder jetting also, processes are inherently omnidirectional, because you inject the binder through two ways. Either it is a thermally activated nozzle, right? There are tiny nozzles where the binder is there, you increase the temperature and a drop of binder falls, or it's a piezoelectric based system. These details you may get later on in some lectures. So this is the droplet, and when it goes back, the droplet falls down on the bottom. So piezoelectric or thermal, whatever it is, these are the source of energy, and they are also parallel to the generation of the droplet. Hence VS and VF are always perpendicular, right? And the droplet is always falling perpendicular to the bed. It is not falling at an angle. Hence process is always omnidirectional. So I think, let me not read the conclusions, and if there are doubts, we can discuss directly instead of I just summarize, because I'm just summarizing what are the methods we have discussed. Instead, we can discuss for 10 minutes. So thank you very much. Please feel free to ask questions.
Yes, sir. This is Mukesh, sir. Sir, my question is that, sir, if we go for a linear deposition using TIG, does omnidirectionality will be maintained, right?
No. Like a wheel, I told you, right? You take a wheel, push it, it can go in one direction without any issue. So directional is only come into picture when you move it in another direction. So in one direction, it won't be Omnidirectionality doesn't matter if you are just moving only in one direction. And that is why, if you remember yesterday, off-axis nozzles were preferable in the case of laser cladding, right? Because they were just depositing in one direction and the cylinder was keep on rotating. Direction was not changing. So if direction is not changing, no, it is fine.
And sir, one more thing. Actually, I wanted to know overall motive of getting one omnidirectional property in DED. Actually, what is our main motive? Actually, sir,
To make the component same at different locations. You move your machine in any direction, you will get same results. That is the goal. That is the whole goal. Meaning to say, even you are making an isotropic part, you produce a part at this location should be similar to the part you produce at another direction. Maybe anisotropic, right? But it should be similar anisotropic, right?
But sir, if you are going for a linear component using TIG, then there will be no problem of like deposition will be remaining the same. It will not disturb like the like type of deposition. It will not disturb that. It will not change the direction of like deposition.
No. Perfectly, you are right. But unfortunately, the things we make are not linear in real life. Otherwise, you are right.
No, sir. I'm taking a case like if suppose I'm in a general depositing a simple wall of
Wall,
using
no issue. Wall, no issue. That is why, Mukesh, there was nobody was talking about omnidirectionality in welding, because welding is always in one direction, right?
No,
so,
sir. In welding, no. I'm telling that I'm depositing a wall like in 3D. Suppose I'm doing one deposition and I'm making component. I'm depositing in Z direction, sir.
Fine.
In one
you will
direction.
not have any
Suppose,
issue.
Sir, what I can do is that I move torch in one direction and return back and again move in the same direction. I am not telling that I will move in the same. I mean, I will trace the path. Then again, I will start from the same point.
You are right. No issues will be there. Okay.
Okay, sir. Thank you, sir.
Okay. So if there are no doubts, I think. Yeah. If you are rich, select the laser. If not, select the MIG. So when I joined here, I also started with MIG. So because, okay, let me put it in a scientific way. If you are dealing with ferrous materials, okay, go with MIG blindly, no issues. And you are not really worried about the material is not really very expensive, right? You deposit with MIG. MIG can give you very high deposition rate. No other process can give. The control is, I mean, you need to just control only one parameter, that is the current, nothing else on the process side. If you talk about TIG, many things has to be varied. You have to vary the wire feeding speed, you have to vary the feed speed, you need to find out where the wire is melting. But the TIG can deposit spatter free. It doesn't really bother much about that. It can. So one way of selecting between TIG, MIG and laser is the accuracy you want on the deposition. Laser could be the most accurate, next is TIG, and least is MIG. Now let me go in reverse manner. If you want to deposit with a high deposition rate, go with MIG, then TIG, and then lastly laser. And then money wise also, I told you, laser is the most expensive, TIG is the next, and plasma is the MIG is the least expensive. Not Yeah, that is true with at least the DC sources. But if you go with a very sophisticated one, CMT welding with MIG is the best one right now, and bit expensive also, cost around 20 lakh. One more question came up, I guess. Now 2 meter, I said that theta lens size. The issue comes with the deflection angle. 2 meter is a very big. Such a big lens is not possible at all to maintain. The deflection angle, it can convert perpendicularly only up to a certain inclination. If the inclination is more, then their beam correction may not be possible. Fine. Now, if the size of the lens, which is not that big also, it is very small. If it is inclination angle is large, you need a larger big mirror, and maintaining that properties everywhere on the lens, it's very difficult. So that is why the lens size is small. Hence, you can't really tilt it much. Now, another solution could be, I'll tell you one, make it very large. Means keep the theta lens very close to the laser beam source, right? And then deflect it. But then the throw distance has to be maintained. Meaning to say, the laser which is coming out of the theta lens has to be collimated. If it is not collimated, means if the diameter is not same always, then the distance is different, and hence you will not get your diameter will be something else. So that optic side create lot of issues. That is the only reason we are limited. But 2 meter, please don't take it. I just give an example. Make a 2 meter big lens, and the issue will resolve. It is not feasible at all. I never said it is 2 meter. Yes, towards the edges of the f theta lens, it's not really very efficient when you put it on the edges. Center it is, so it's just a correction, not really exact solution. Thank you.